Okay, welcome to chapter 16. In this chapter, we talk about the magnetic fields. In the first video, we will talk about the introduction of magnetic field and magnetic force on a moving charged particle. Okay, so let's start now. This is a bar magnet, and then this is North Pole. This is South Pole. We know that the magnetic field lines will point out of the North Pole to the South Pole. And then if you put a compass here, the compass will have a needle that points along the direction of the magnetic field lines. And therefore, in this case, we know that the compass will point to the direction of a South Pole. That means that it will point along the magnetic field line. But then we know that in a compass, the needle of the compass should point to the direction of north. Then what is going on? Actually, on the Earth, we know that the geographic North Pole is actually equivalent to the magnetic South Pole. That means that we know that the geographic North Pole is very near to the magnetic South Pole. And then the geographic South Pole is very near to the magnetic North Pole. So actually, this is magnetic North Pole. This is magnetic South Pole. You know that the magnetic field line will point from the magnetic North Pole to the magnetic South Pole. So in this case, we know that the magnetic field line will point along this direction. And then the compass will point to the geographic North Pole. So you know that on a compass, the needle points to N, which means geographic North Pole, but which is actually magnetic South Pole. And then you also know that there is an angle between the geographic poles and also the magnetic poles. And then this angle is actually not a constant. That means that this angle is a variable, and then this angle will change every year. Okay, recall that in the chapter electrostatic, you only learn about the electric field strength, which is capital E. And then we also call electric field strength as the electric field intensity. Okay, you do not learn about electric flux density in the chapter electrostatic yet. But then in this chapter, we also only learn about the magnetic flux density B only. H, capital H, is the magnetic field strength, or you can also call it magnetic field intensity. But then in this chapter, we don't learn about the magnetic field strength. We only talk about the magnetic flux density. Okay, the purpose of me telling you all this is that I don't want you to say that B is the magnetic field intensity, because B is only magnetic flux density. Okay, B equal to mu H, and then mu is the permeability of the medium. The permeability of the medium is an indicator of how much the medium allows the magnetic field lines to pass through. Okay, same as here, the permittivity of the medium is an indication of how much the medium can allow the electric field lines pass through. Okay, so you know that, of course, the higher the magnetic flux density, the higher the magnetic field intensity. Okay, because they are directly proportional. Okay, so in the last chapter, when you know that the expression for the electric field is this, then you know that the expression for D is so you know that the expression for the electric flux density is Q over 4 pi r squared, and then the expression for the electric field intensity is Q over 4 pi epsilon squared. So I want you to remember that actually the magnetic flux density is just like the electric flux density. And then the magnetic field strength is just like the electric field strength here. But then in the chapter of electrostatic, you only learn about the electric field strength. And then in this chapter, you also learn about the magnetic flux density only. Okay, in the chapter of electrostatic, you learn that the electric field strength can be represented by the density of electric field lines in that region. That means that, for example, you choose this region, you know that there are a lot of electric field lines here. And then if you choose this region, you know that there is very little electric field lines here. So you can say that the electric field strength here is greater than here. And then you also realize that the electric field lines will never cross each other. Okay, so by the same reasoning, here you can also do the same. That means that, for example, if you want to choose this region, you know that there is now 1, 2, 3, 4, 5 lines in this region. And then maybe now you choose here. Now there are only 2 lines in this region. So you can say that the magnetic field strength here is much greater than the magnetic field strength here. That means the magnetic flux density here is much greater than the magnetic flux density here. And then you also notice that the line will never cross each other. And then actually, I need to tell you that actually, in the chapter of electrostatic, you know that you can have an individual charge. That means that you can have a positive charge without having an negatively charged particle. And then you also can have a negatively charged particle without a positively charged particle. Okay? But then, in the chapter of magnetic fields, you have to know that so far, we can never see a north pole without a south pole. That means that the monopoles do not even exist. You really have to have an end pole. Then only you can have a south pole. Okay, that means that the monopoles do not exist in the chapter of magnetic field. You really have to have a north pole in order to have a south pole. You cannot say that you want the north pole only and then you don't want the south pole. Okay, because the monopoles do not exist in magnetic field. But then the monopoles can exist in the electric field. That means that you can have this charge without this charge. You can have this charge without this charge. Okay, so we talk about the force on a moving charged particle now. A particle of charge Q moving with a velocity v in a magnetic field of magnetic flux density B experiences a magnetic force of F equal to Q v cross B. And then the Q is positive 1.6 times 10 power negative 19 coulomb for a proton. And then E is negative 1.6 times 10 power negative 19 coulomb for an electron. Okay, so now we can express this expression in this form. This is a modular sign. That means that we only care about the magnitude of V. This is also a modular sign. That means that we only care about the magnitude of B. Okay, and then the angle is the angle between V and B. So you know that B is like this. And then this is actually the definition of a magnetic flux density. That means that if you are asked to give the definition of the magnetic flux density, then this whole thing should be your answer. The magnetic flux density B of a magnetic field is the magnetic force on a charge of 1 coulomb moving with a velocity of 1 meter per second at right angles to the magnetic field. Okay? So before this, I want you to know how the symbols work That means that how the symbols come from. Okay, this is an arrow. If the arrow is coming to you, you will only see a dot like this. Okay, so if you see a dot like this, you know that the direction is up of the page. If you are the one who shoots the arrow, that means that the arrow is coming away from you. Then you will see a cross like this. Okay, so next time when you see a symbol like a cross, you know that the direction is into the page because it is shot by you. Okay, so now if a proton comes perpendicularly to a region of uniform magnetic field, that means that now the magnetic field is into the page, and then the proton is moving here. Then the proton will move in a circular path. You use the Fleming left hand rule. That means that this is your thumb, this is your first finger, and this is your second finger. And then they are all at right angles to one another. F, B, V. If this is pointing towards the direction of the magnetic field, and then this is pointing to the direction of the velocity of the particle, then this is the magnetic force. That means that this is the direction of the magnetic force that acts on the positively charged particle. Okay, so in this case, B is into the page and then V is here. So you know that the F is in this direction. Okay, so you know that a proton will move in a circular path in this case. So this is an electron. The electron has the opposite charge compared to the proton. So just now from this expression, we know that when Q has another sign, then the F will have another sign. Okay, so you know that the proton will move in an anti-clockwise direction, and then the electron will move in a clockwise direction. You also use a Fleming left-hand rule. This is B, and then this is V. But then for the electron, since it has an opposite sign, that means that the force has an opposite sign also. That means that the force is here. Remember, in both cases, the force will always point to the center of the circular path. Okay, because the magnetic force is actually the centripetal force. Okay, so you know that the direction of the force must be towards the center of the circle at all times. Okay, so F equal to ma. The centripetal acceleration is actually equal to r omega squared, which is equal to v squared over r, which is equal to v omega. V is the linear velocity, r is the radius of the circular orbit, and then omega is the angular velocity. Okay, so actually you check the dimension is correct because radian is just a unit. Okay, that means that this one, the radian, has no dimension. Okay, so now normally we choose these two because we know the radius of the orbit very well. But then if you want to use v omega, is also okay, but then we really seldom use this kind of expression. Okay, and then you know that the magnetic force is actually the centripetal force, so you know that radius is given by this expression. 1 period is the time taken for the charged particle to complete one oscillation. That means that the time taken for the electron from here to here again. Okay, so the period is equal to the distance moved by the charged particle in one cycle divided by the linear velocity. Okay, so you can substitute r here, and then you know that the period is like this. The frequency is 1 over period, and then one frequency is actually defined as how many oscillations can be completed per second. Okay? Just now, you know that the expression for t is like this. So you know that t is actually independent of velocity. So for example, let's say now this is an electron. Okay, you still use your Fleming left hand rule to check whether your direction is correct. Okay, B is into the page and then V is here. So you know that F is supposed to be here, but then since the electron is of opposite sign, that means that the force should be here. Okay, the force should be here, which is towards the center. Okay, this is the magnetic force acting on the electron when the electron is here. Okay, so if the electron is here, that means that the Fn should be pointing this way. Okay. Okay, so you know that in this case, the radius is r. In this case, the radius is 2r. But then in this case, the velocity is v. And then in this case, the velocity is 2v. So you know that the time taken for the electron here to complete one oscillation is equal to the time taken for the electron to complete one oscillation here. That means that they will move like this. Okay, although this is smaller, but then the electron moves slower. Although this is a larger path, but then the electron moves faster. Okay, so you actually know that T depends on M, B, and Q only. The mass of the electron is 9.11 times 10 power negative 31 kilogram. The charge of the electron is negative 1.6 times 10 power negative 19 coulomb. So you know that actually T is inversely proportional to B only. But then in both cases, the B has the same magnitude. So you know that the period here is equal to the period here. Okay. Just now, in this case, if the electron is moving at the velocity v, that means that the velocity here is v, the velocity here is v, the velocity here is also v, the velocity here is also v, the velocity here is also v. And then in this case, if I say that the velocity is 2v, that means that the velocity of the electron here and here and here and here and here are all 2v. So you know that the charged particle has a constant velocity, and therefore we want to question why the charged particle cannot be accelerated in a magnetic field. The magnetic force is always perpendicular to the displacement of the charged particle. Okay, for example, the displacement of the electron is from here to here, and then the force is here. That means the displacement of the electron is from here to here. Okay, this is the displacement, and then this is the force. So you know that they are perpendicular at every point on the circular path. Okay, for example, for here, the displacement is here, and then the force is to the center of the circular path. Okay, so you know that F and ds are always perpendicular to one another. So you know that the magnetic force and the displacement is always perpendicular. So that when you use the expression for the work done, which is F dot ds, then you know that the work done is actually 0. That means that no work is done by the magnetic force on the charged particle. And therefore, there is no change in the kinetic energy of the charged particle. So we say that there is no change in the speed of the charged particle. Okay? And then the speed of the charged particle remains constant. Okay, just now you learned that F equal to QV cross B. If you don't want to use Fleming left hand rule, then you can also use your right hand grip rule. You use the right hand to find out the direction of V cross B. Okay, first, for example, in this case, you use your four fingers to move in the direction of V, and then your four fingers must curve in the direction of the magnetic field. And then this time your thumb finger will point along the direction of the magnetic force. Okay, let's do some question. An alpha particle which is moving in a positive y direction in the region of uniform magnetic field is shown. Okay, the magnetic field is pointing here, and then your alpha particle is moving from here to here. What is the direction of the magnetic force acting on the alpha particle? First, you can use your Fleming left hand rule. Okay, FBV. B is here, V is here. Then you know that F is into the page. Okay, but then actually I don't encourage the student to use your Fleming left hand rule a lot, because I actually prefer you to know from this equation, and then you can use your right hand to find where is the direction of V cross B. Okay, for example, your four fingers must move in the direction of the V, and then you cross to the direction of the B, and then this time your thumb finger is pointing into the page, so you know that the F is into the page. Okay, if you want to use Fleming left hand rule, sometimes the student find it very difficult to orientate their fingers to the orientation of the figure. But then if you use the right hand grip rule, then you just use your four fingers to point in the direction of V, and then you try your best to curve to the direction of the B, and then your thumb finger will point to the direction of the magnetic force on the positively charged particle. Okay, alpha particle is 4,2 helium charged particle. Okay, that means that alpha particle is a positively charged particle. Okay, so let's say now this is an electron. If this is the electron, then of course the direction of the magnetic force is out of the paper. Okay, so when you are trying to figure out the direction, you have to make sure that the particle is positively charged. A charged particle passing through a region of magnetic field moves in a straight line. State the direction of the magnetic field with respect to the motion of the particle. Explain your answer. Just now we know that in a magnetic field, the charged particle will move in a circular path, but then now it moves in a straight line. So that means that no magnetic force is acting on the charged particle. If there's no force acting on the charged particle, you know that the direction of the magnetic field is parallel to the direction of motion of the particle. Because from the equation F equal to QVB sine theta, if the V is parallel to B, that means that if V has the same direction as B, then theta is equal to 0 degree. So sine 0 degree is equal to 0. But then if V is opposite to the direction of B, then it is 180 degree, and then sine 180 degree is still equal to 0. So that means that you know that the direction of the magnetic field is parallel to the direction of motion of the particle, because the particle moves in a straight line. An electron moves with a speed v near a bar magnet. Which diagram shows the electron experiencing the maximum magnetic force? Okay, F equal to QVB sine theta. So you know that the higher the value of sine theta, the higher the magnitude of the magnetic force acting on the electron. So here, you know that the B is here, and then the V is here, and then the theta is 90 degree. So sine 90 degree equal to 1, which is the maximum value of the sine function. For example, here, you know that the electron is moving parallel to the direction of the magnetic field. So you know that it is sine 0 degree, which is equal to 0. So you know that there's no magnetic force acting on the electron in this case. For example, in this case, you know that the electron is also moving tangential to the path here, okay, which is tangential to the magnetic field lines of the bar magnet. So you know that sine 0 degree equal to 0. That means that no magnetic force is acting on the electron here. Okay, in this case, the angle is quite small, which is about maybe 60 degree. But then you know that sine 60 degree is still less than sine 90 degree. Okay, so in this case, there's only some magnetic force acting on the electron. And then in this case, the magnetic force that acts on the electron is maximum. The path of two charged particles X and Y which enter a uniform magnetic field perpendicularly with the same velocity are shown. Okay, the Y will move from here to here, the X will move from here to here. Okay, then the direction of the B is into the page, which is true of the charges of the particles X and Y, and the magnitude of the specific charge, that's the ratio of charge to mass of particles X and Y. Okay, so you know that F equal to ma, and then the force is the magnetic force, and then the A is the centripetal acceleration. Then you know the expression for the radius of the circular path. Okay, so you know that the radius is inversely proportional to charge to mass ratio. Okay, charge to mass ratio is the specific charge. Okay, so you know that the circle of Y is like this, and then the circular path of S is like this. That means that Ry is larger than Rx. Therefore, Qy over My is less than Qx over Mx. Okay? Because when Q over M decreases, R increases. And then you use your Fleming left-hand rule. You know that B is into the page and then V is here. Okay? So, for Y, you know that it's a positively charged particle because the force is to the center of the circle. And therefore, you know that X is a negatively charged particle because when B is like this, V is like this, the F is downward, which is here. Okay, so this is the circular path of X. Okay, and then this is the circular path of Y. Okay, so answer is B. A positively charged particle P and a negatively charged particle Q are projected into a magnetic field at the same speed. If the magnitude of the charges are the same and the masses mp equal to 2mq, which diagram shows the correct paths of P and Q in the magnetic field? Okay, from this expression, you know that the higher the mass, the larger the radius. So when mass of P is very large, therefore the radius of P should be very large compared to the radius of the Q. Okay, so if MP equal to 2mq, then RP equal to 2rq. And then you know that the P is positively charged. That means that if you use a Fleming left-hand rule, if this is P, this is the direction of the magnetic field, and then this is the direction of the velocity. Therefore, the direction of the force is here, okay? Which is to the center of the circle. And then you know that Q is negatively charged. That means that the force will be opposite, okay? That is, the force on Q is here. So you know that the positively charged particle will now move anti-clockwise, and then the negatively charged particle will move clockwise. The track of a charged particle in a magnetic field is shown. Okay, you know that it's a spiral shape. Which statement is true about the particle? Okay, so by using this expression, you know that R equal to mv over bq. And then when the radius is decreasing, that means that the particle is moving in a smaller and smaller circular path. Then you know that the speed of the particle is also decreasing. Okay, and then from the Fleming's left-hand rule, you know that, for example, in this position, if the magnetic field is into the page and then the velocity is here, the force should be here for the positively charged particle. But then for a negatively charged particle is the opposite direction. So you know that this is a negatively charged particle, and then the V is decreasing. Which statement is true when a charge moves in a uniform magnetic field? It will always experience a magnetic force, not necessary. If V is parallel to B, that means that F equal to QVB sine theta equal to QVB sine 0 equal to 0, then the magnetic force is 0. That means that it might not experience a magnetic force. It will always move with a constant velocity. Not really. Because sometimes there might be some frictional force, because when the magnetic field is in the air, then most probably your electron will feel some frictional force when it collides with the other particles or anything else. Okay, for example, in this case, you know that the velocity is decreasing. Why the velocity is decreasing? Maybe the electron is clashing with some other particles or something else. Okay, so maybe in a uniform magnetic field in the air, then the velocity can be decreasing when the particle actually clashes with the other air molecules or whatever in the air. It will gain kinetic energy due to the work done by magnetic force? No, we just now know that the magnetic force that acts on the charged particle will never have any work done onto the charged particle, and therefore the charged particle can never be accelerated by the magnetic field. Its path is circular when it moves perpendicularly to the direction of the field. Yes, because that you know the magnetic force will provide the centripetal force. Okay? A proton moves in a circular path perpendicularly to a constant magnetic field strength of 4.0 times 10 power negative 3 Tesla. If the momentum of the proton is 1.52 times 10 power negative 23 kilogram meter per second, please determine the radius of the circular path. F equal to ma. Okay, by using this formula, you can arrive at this. And then mv is actually the momentum of the charged particle. Okay, so you are now given the momentum. That means that you are now given the value of mv. So you can find the radius. Find the speed of the proton. Okay, you know the momentum equal to mv, and then mass of the proton is 1.67 times 10 power negative 27 kilogram. Show that the orbital radius of a charged particle of mass m and charge q moving at right angles to a magnetic field B can be written as this one, where k is the kinetic energy of the charged particle. Okay, you really have to know that momentum equal to square root 2 mk. Okay, and then just now you know that the momentum is mv, so the momentum is square root 2 mk, and therefore you can arrive at this equation. Okay, so in the next video we'll be talking about the magnetic force on a current carrying conductor. Thank you.